ready to start? Okay, so welcome everybody for the afternoon session. We will tell us about large deviations for arithmetic progressions.
Thank you for the invitation. It's a pleasure to be here. So today I'll talk about large deviations for arithmetic progressions. So what I will talk about is based on joint work with Bashwar Bhattacharya, Shashandu Ganguly is here, and Fernando Xuancheng Xiao, who's also here. Okay, so the main problem I'm interested in is the following. I will let xk denote the number of k-term arithmetic progressions in a random set of 1 to n. So what do I mean by this? So bracket n means numbers from 1 to n, and the subscript p means that every element chosen appears with probability p independently. And I want to understand properties of this random variable. It will be helpful to also talk about the analogous problem in random graphs, where for a fixed graph h, I'm looking at the quantity, which is the number of copies of this graph h in a random Ayers-Renier random graph, GMP. Both these quantities, at least in the regime that I care about, are asymptotically normal. So if you subtract the mean divided by the standard deviation at n go to infinity and p appropriately, then it will converge to a normal distribution. But what I want to talk about is what happens if we look much beyond the standard deviation. And in particular, we wish to estimate the tail probability that x, this random variable, exceeds its expectation by some constant factor. Okay. So throughout, delta will be some fixed number, and n goes to infinity, and p will be a function of n, and usually going to 0, perhaps not too quickly. So this has a long history. Sometimes it's known as the infamous upper tail. There are lots of developments in probabilistic combinatorics which are motivated by trying to come up with techniques to better analyze problems like this. In particular, Jensen Ryshinsky, Kim Wu have all developed various improvements in tail bounds and concentration bounds with this problem as one of their central motivations. There was a recent survey by Sharav Chatterjee in the Bulletins of AMS with a very nice summary of some of the more recent and exciting developments regarding this problem. I want to begin by first stating some of the results, both for arithmetic progressions and also for random graphs, just to tell you what we now know about this tail probability. And then in the second half of the talk, I will focus on arithmetic progressions and focus on a particular aspect of our solution that may be of more interest to structure versus randomness in additive combinatorics. So for graphs,
so you think it doesn't matter how exactly you count the...
It doesn't really matter so much. There are small errors that don't appear in the final answer.
It can be induced as well.
Yeah, but when I write this, I usually mean not induced. But yeah, it doesn't really make a big difference in what I will say next. Yeah, so non-induced for the rest of the talk. For graphs, even the order of this, the logarithm of this probability was not determined until just a few years ago. In work of Chatterjee and independently DeMarco and Kong, they showed that if p is at least some constant times log n over n, then we have the following asymptotics. So just for the case of triangles, so for K3, just for triangles, the number of triangles that appears in a random graph, the probability that this quantity exceeds its expectation by a constant factor has the asymptotics p raised to some constant depending on delta, n squared p squared. Let me give you a very quick proof of the lower bound of this probability. Basically, if you plant a clique on some number of vertices, and if you choose the number of vertices to be on the order of np, then you see that from this clique alone, if you force that clique to be in there, that alone will generate enough triangles to get you the deviation that you're looking for. So just having this clique there alone is enough. And what's the probability that this clique occurs? Well, this clique occurs with probability p raised to the number of edges in the clique, which is this quantity here. Okay. So that shows you that the probability is at least the right-hand side. The other direction is much more intricate, and it took a long time before this result was established. This asymptotics was later extended by DeMarco and Kong to from triangles to cliques of any size. But in general, for a general H, the strongest type of this result is not yet available. Now let me talk about the analogous result for arithmetic progressions. So this is fairly recent work due to Lutz Wernke. And he showed that if p is at least some constant times log n over n raised to the power of 1 over k minus 1, then the number of k-term APs in a random set the probability that it exceeds its mean by a constant factor has the asymptotics p raised to some constant depending on k of square root of delta n squared p to the k. So in some sense, this result is even slightly better than that of than the one for triangles, because Wernke correctly identifies the order, the dependence on delta. So there's a constant that is missing here. Again, let me give you a very quick proof of the lower bound. Just instead of planting a clique, let me just plant an interval of length roughly this quantity here. You plant an interval of that length, that interval alone generates enough arithmetic progressions to get you the large deviation, and the probability that this interval is present is p raised to the number of elements, precisely this expression here.
So for the lava tails, the tails are not symmetric here.
Right.
The lower tail is easier and it's different, correct?
Okay. So the lower tails, that's right. Traditionally, the lower tails were obtained easier, more easily, or at least earlier, due to Jensen's inequalities. I'm not going to talk about lower tails for this problem in this talk, but at the level that I want to discuss, which is what happens to the constants, how do you identify the constants here, the lower tails actually seem more mysterious. And this may be related to extremal problems. For example, consider the following classical extremal problem. Fixed in a graph of fixed edge density, what is the maximum and minimum number of triangles? Okay, so maximum comes from a clique, Krysko-Katona, and minimum is the result due to Rasparov, and that's much more intricate. So upper and lower, they're different, and that kind of difference also shows up in this type of problem as well. And we don't understand the lower tails at that level yet, but you're right. If you just want to get some result of this type just for the order, then the lower tail was obtained earlier. Okay. So the goal for the rest of the talk is to discuss the methods and results concerning identifying the constant that appears here. Right? What is the constant that is hidden in these expressions here? Well, okay, so you might ask, why do we care about these constants? Well, first of all, for any practical applications of such tail bounds, these constants basically never matter. If you have bounds of this form, either it's good enough for your application or knowing a better constant probably won't help. But there is, I think, a much better reason to care about these constants, which is that it tells you something about the typical structure of a set conditioned on the random event. You might care about the following question. If I give you a random graph, and I tell you, in other words, I condition on the real event that it has lots and lots of triangles, what should you expect this graph to look like? In other words, what is the main reason for seeing lots and lots of triangles? What is the main reason for seeing lots and lots of three-term arithmetic progressions? Could it be that you saw lots of triangles because there was a clique that appeared in this graph, or maybe some other reason? And results of this form point you to that kind of observations. So there is a connection there that I won't go into detail, but I think that's maybe a better reason to care about these, what I will say next, namely identifying the constants, understanding the typical structures. Yeah.
So do we have theorems of this nature?
Yeah, so I'll say something. And
Structure, I mean, that's really
yes, so only for constant p, not so much for p going to 0. So the question is, identify the constants. There were some very exciting recent developments that provides techniques for analyzing such problems, and they go under the name of nonlinear large deviation principles. And a nonlinear large deviation principle is, in some sense, a tool that converts such questions and reduces them to certain variational problems, or in other words, extremal problems. For this type of problem, the first result of this form is due to Chatterjee and Varadhan, where using Simoraides' regularity lemma, they managed to establish such a nonlinear large deviation principle in the case of constant p, at least in the setting of graphs. There was an important breakthrough in the subsequent work of Chatterjee and Dembo. So just appeared last year, but appeared on the archive several years earlier, which brought, so using a completely different method, that brought this range down to allowing p to go to 0 as n to minus some small constant. And this is for graphs and also three-term arithmetic progressions. Very recently, this past December, Ronan-Audin provided, using a completely different method, using tools from stochastic calculus and control theory, such a nonlinear large deviation principle that provided a wider range of applicable p, but still of this form. So I want to talk about some results where, so in our work, we first solve the variational problems, and that gives the precise constants that I will state momentarily. But we also look into these large deviation principles and provide such a principle for the case of k-term arithmetic progressions. And I'll talk about some of the limitations and obstacles that we've encountered that may be of interest for those of you who are interested in problems in additive combinatorics. So now let me state the results. For graphs, so in the case of triangles, we initially looked at this with Eyal Lubetsky, but also for triangles and for cliques of any size. And the subsequent work, the joint work with Bhattacharya, Ganguly, Lubetsky, and myself, we were able to obtain this result for OH, and the result has the following form. If P goes to 0, so H is now fixed, right? So fix your graph H. If H is fixed, and okay, so it's important that it's not induced. Right? So this is just for counting the number of subgraphs isomorphic that are H. If P goes to 0, but no quicker than n to minus some small constant log n, and this alpha, take alpha to be 1 over 6 times the number of edges of H. And this is due to, so this limitation here is due to the recent work of Eldon. Previously, there was a smaller range because we used earlier results. Okay, so we were able to identify an explicit constant called CH of delta that completes this asymptotic. Here, delta is, so this capital delta is the maximum degree of H. And just as an example, when H is the triangle corresponding to this case here, this constant is actually the minimum of 2 different expressions. One of them is delta to the 2/3 over 2, and the other is delta over 3. And the reason that there are 2 different expressions there is that if we look at the construction here, so previously I said one of the ways of generating lots of triangles is to plant a clique. And you can ask, well, is that the only way to do it? Well, actually, there's another way that's also competitive. It's not just planting a clique, but depending on what your value of delta is, there may be a better way to do it. Namely, if delta is large, delta is, let's say, larger than 27 over 8, then, okay, you can plant a clique, and if you work out exactly how big of a clique do you need, you find some expression, okay, plant a clique of that size, and that gives you enough triangles, and the rest you leave as GMP unchanged. However, when delta is less than 27 over 8, then there's a better way to do this. Namely, you find an even smaller set of size, say 1/3 delta p squared n, and then you connect this set to everything else in your GMP. Okay, so you plant this object here. Take a small set of vertices and connect that set to everything else in your graph. This also generates lots and lots of triangles, because for every edge of GMP, you automatically get a triangle from that edge to every one of the vertices here for free. Okay, so you get lots of triangles here. And if you work out the parameters, turns out for larger values of delta, this is more advantageous. And for smaller values of delta, this is more advantageous. And we have similar results for general H. It turns out, in general, you also have this kind of dichotomy, but only if H is regular. When H is not regular, this option is not available. But for triangles, you have another H regular graphs, you have this dichotomy. Right, so that's for graphs. Now let me say what are the results for arithmetic progressions. So this is the work.
So
Yep.
are we expecting a stability theorem as well?
So I can only promise the asymptotic in the exponent. So one could perhaps dig further into the proof to obtain some kind of stability, but I can't promise any theorem of that form right now. And I don't even really know how to state a theorem or even a conjecture of the form conditioned on this, the graph looks like something. What does look like mean? I don't know what's the right language even.
You can modify specify only a few pairs and then you get either this or
Sure. Yeah, so something along those lines, but I don't have a good conjecture in mind.
cut.
Yeah, but cut norms are good for dense graphs. Here, yeah, so for p constant, we do have a statement of that form. So for arithmetic progressions, this is the work that I'll talk about for the rest of this talk. The asymptotic is the following. Again, k is always fixed, just like h was always fixed there. If p goes to 0, and p goes to 0 not too quickly, then, well, okay. In the case of graphs, there were a bit of a surprise. There were two possibilities that could come up. In the case of k-term arithmetic progressions, actually the story I told you here is the correct one. That's the only thing that could happen in the sense of if I just care about the leading term in the exponential asymptotics. So it's equal to p times 1 plus little 1 of this quantity here. Okay, so this is precisely the story I told you over here. But now we have the correct constant. So we were able to prove this, well, in the case when alpha if k equals to 3, we can take alpha to be 1 over 18th. So 3 and 4 are slightly special cases. And in general, k, we can get something like 1 over 6k squared, 6k k minus 1. So as you see, it's not the end of the story. Warnke's result tells you can take down to around 1 over k minus 1 action. Below that, we also know the asymptotics, and it has a different form. Here, it would be nice even to reduce this dependence from quadratic to linear. So there's a bit of a gap. So it's not the end of the story. And much of this comes from limitations in what we currently have available as nonlinear large deviation principles. So there are some inefficiencies in these methods here. But also, there are some inefficiencies in the additive combinatorics analysis that we'll talk about in the second half of this talk. But let me pause to see if there are any questions.
With the little one in the exponent, that's with p going to 0, right?
So p goes to 0 as some function of n.
Right, but like for fixed p and for triangles, like there's a central limit theorem, right?
There's a central limit theorem, but it doesn't tell you what happens for large deviations.
Okay, so some weird phenomenon does happen for large deviations,
Right.
which you can analyze when p is going to 0.
Yeah, so for example, you look at this form here. You don't see this, and this is not Gaussian.
Yeah. Okay.
Any other questions? Yep.
Just to clarify, so for your resultant graphs, so this is proven for every graph H? No.
For every graph, oh, okay. Yes, we have the result for every graph H. You give me an H, I can give you a constant.
And the constant for every graph H will arise from the lower bound coming from at least one of those two examples? Or are there more exotic for like non-regular?
Okay, so just to be precise, let's say H is connected. Okay, so let's say H is connected. If H is regular graph, every vertex has the same degree, then you have these two possibilities. And you check if delta is bigger than some threshold, then this possibility, otherwise that possibility. If H is not regular, don't worry about that. That never contributes meaningfully. Just look at that. If H is not connected, the story is more or less the same as this, but slightly more complicated.
Maybe it's obvious to other people. Why is it important that p tends to 0? Why?
If p doesn't tend to 0, if p is a constant, actually you get into a different kind of extremal problems. And in general, we do not know what the constant is. And that's a whole different story for another talk.
So the standard way to get more copies of H is to plant something dense.
Mm-hmm.
Suppose I forbid you to do this by limiting local density.
Sure.
So you know what's the result?
I don't know. You can formulate a variational problem of that form, but I don't know what the result is. In fact, that may be related to what Alan was asking for a constant p. In fact, maybe through some transference principle, you can reduce that problem to a constant p. Okay, so these are just the statements of the results. Now let me move on to the second half of my talk, where I will focus on the arithmetic progression case and tell you one aspect of the solution and the difficulties that we've encountered while working on this problem. So let me write T3. So for x being an n-dimensional vector, let me write T3 to be the 3AP count of x. What we need to understand, it turns out, is that we want to control the complexity. Okay, and I'll be somewhat vague here, but make it more precise later. We want to understand the complexity of the set of gradients of this function t. Okay, so gradients in the sense of calculus, so the gradient of a function is the vector of its partial derivatives. In particular, because this is a polynomial, the gradient has the following fairly nice form that if I look at the inner product of the gradient with another vector, and this is obtained by taking this expression and replacing one factor of x by y at a time. And this is the reason that sometimes I'll interchange saying gradients and dual functions. So I can think of these as dual functions, what is dual to one of the factors. And they play essentially equivalent roles. In Chatterjee and Dembo, they showed that if you have a function, for example, the number of three-term arithmetic progressions or the number of graphs in a number of subgraphs, if the function in some sense has low gradient complexity, in the sense that how many or what is the set of all possible vectors that could appear as the gradient of this function? Well, generically, it could be the entire box of vectors, but in reality, it's a much smaller set. If you can somehow control what kind of vectors could appear as gradients, then you can get some control on these large deviation inequalities. And Eldon refined that type of analysis using a completely different method. So Eldon's work uses methods coming from Brownian motion, and roughly, one way to think about this is quite a bit of a lie, but one way to think about this is that you can do some sampling of this space to try to sample your rare event. And the sampling involves some kind of gradient descent. And if you can accurately control what the possible set of directions you have to go in this gradient descent, then that gives you a lot of control. And that kind of control is very useful for generating results of this form. That's very much a lie, but we can leave it at that and move onward. What do I mean by the complexity of the set of gradients? In Eldon's work, his notion of complexity that's relevant for our application is that of a Gaussian width. So if I give you a set or a body in n space, then the Gaussian width of the set is defined to be, well, if I take a random Gaussian vector, n-dimensional Gaussian vector z, what is the maximum correlation of z with your set. So that's the definition of Gaussian width. A couple ways to think about it. One is that this is essentially, okay, so a random Gaussian vector is basically a random unit vector multiplied by root m, roughly. So this is saying what is the mean width. So if I pick a random direction, what do I expect as the mean width of your set multiplied by root m? Another way to think of it is that if your k is a finite set of points, then each point comes with an associated Gaussian random variable, and different points, so this is a Gaussian process, and different points, the random Gaussians that correspond to them are correlated, and I want to know what is the maximum of this Gaussian process.
Are you assuming that k is centrally symmetric or not necessarily?
It doesn't really matter. Yeah, it doesn't, because, yeah, it doesn't matter. So here's a question. So what is the Gaussian width of the set of gradients of that function there? So this normalization is chosen so that this quantity as a vector is L infinity bounded.
So presumably TK is the same thing as K, right?
Yeah, so TK, right? So this is T3. So TK is this for k-term arithmetic progressions. Let me denote this quantity as a shorthand, just writing it as GWK. Okay, so we want to understand what is GWK, find estimates on GWK. Yep.
Sorry, you might have said this, but do you mean in the soup or the soup of the absolute value of the?
It doesn't matter. It doesn't actually matter. Yeah. I mean, if you like, you can think of it as a soup of absolute value, but yeah, it makes no difference. Let me offer some trivial bounds.
Wait. Sorry.
Yeah.
I don't understand it. So this gradient, it's a point, so you go.
No, this is a vector. Each gradient is a vector. So each gradient is a vector, and because of this normalization, each gradient is a vector with bounded coordinates. And so this lies in some, let's say if I do some scaling, this lies in some unit box, and ask, what's the Gaussian width of this unit box, or this subset of the unit box? Okay, so let me offer some trivial bounds. First, it's at least some constant times root n. The question? At least some constant times root n, and that's just because if I look at just one element, right? So if I look at y, just the constant vector y, then already you see that this corresponds to a sum of Gaussians. And if I say, look at that and look at the zero vector, so that's just the sum of Gaussians as fluctuation root n. On the other hand, it's at most some constant times n because, well, everything's L infinity bounded, and the sum of absolute values of n Gaussians is of order n. Okay. We would like to better understand what this quantity is, and any improvement to this upper bound, this trivial upper bound, would be good. Right? So any power-saving improvement here, when combined with the machinery Aldon, allows you to take some positive exponent here.
In particular, K during the period.
So K will be a constant. So for each K, the fixed K. I'll talk about different Ks, but all the implicit constants may depend on K, and K will always be a constant. So here's what we conjecture this Gaussian width to be. So fixed K, so K is always fixed, and I'll omit dependence on K from the asymptotics. This really should be about root m. and maybe give it some extra log factors. In fact, maybe even just n root of n log n would be enough. And this is certainly true for k equals to 3. And I'll show why this is true for k equals to 3. And k equals to 3 is the only k for which we know how to prove this. Right? In the other cases, we know only weaker bounds. Okay, so let me prove some results towards this conjecture. I should also mention that in the case of, so I'm talking about this in Z mod n or 1 to n, but if you care about finite field setting, this should not be correct. Maybe you need some extra, some bigger constant there. First, let me give you a very quick and cheap bound, a cheap upper bound that improves this trivial bound. Namely, by noticing that this correlation of tk, the gradient of tk and y, okay, so this expression here. So one of the standard tools from additive combinatorics that's very commonplace nowadays is the Gowers-Cauchy-Schwarz inequality that bounds such a quantity. If you do the appropriate normalizations, I'm being rather sloppy here, it's bounded by some Gowers uniformity norm. And you can estimate what is the Gowers uniformity norm of a random Gaussian vector. And that gives you a bit of power saving. And this allows you to prove that GW is big O of n to the 1 minus 2 to the k minus 1. So it's something, but the dependence here is quite far from polynomial dependence on k. So what we were able to show is, well, so GW3 is that, and so GW4 is also a bit of a special case. It's roughly n to the 4 3/4, extra small log factor. And GWK is n to the 1 minus 2 times k minus 1. K at least 5. I mean, this is also true for k 3 and 4, but these bounds are somewhat better. I should mention that this problem is very much connected to another problem in additive combinatorics, namely understanding similarities theorem with a specified set of random differences. So if I give you a random set of integers and ask, is there a similarities theorem where if you take a positive density subset of integers, can you find a 3-term arithmetic progression with difference in your prescribed random set as your differences? So that's a problem that's very much related to this one. And much of our techniques that were used to prove this are essentially analogous to results in the similarities theorem for random differences. The main strategy is to, well, here's a simple fact. And from this, I'll say what the main strategy is. If I have a set contained in the unit box, and if it's not too big, then the Gaussian width is not too big. So a small set of points has small Gaussian width. So this just comes from each Gaussian is concentrated, and you take union bound. So this is easy to prove. And the strategy is to contain your set of gradients in a small convex hull. So contain the set of gradients in the convex hull of a small number of L infinity, so coordinate-wise bounded points. Okay, so what does small mean? Ideally and conjecturally, we would like to use only polynomially number. So we don't know how to prove anywhere close to that. Okay, I'll make this conjecture more precise in a second. Okay, if you're not used to thinking about gradients, here's a slightly different but equivalent formulation that's more familiar in the language of additive combinatorics. So suppose looking at functions from intervals to the reals, and I define this operator lambda, which essentially tracks the number of k-term APs this red conjecture here, rephrase it as the following. Fix k. Then there exists a set, capital Phi, of functions, say bounded functions on the interval. And this set, capital Phi, is fairly small, let's say polynomial in size, such that whenever you have bounded functions, and I have some g, and I want to understand this quantity here, then this quantity is always bounded by only looking at correlations of g with one of your bounded functions. So I'm only looking at dual functions. So functions looking at let's say in the 3AP form, cover one of the factors, look at the dual. And I'm saying, as I range over all the possible duals, initially you need to look over very many functions. So imagine this is instead of interval just 0 or 1. Initially you need to look over 2 to the n, maybe many functions. But what this conjecture is saying is that if you just care about upper bounds, then you can find a much smaller convex cover of polynomial size.
So, but isn't this parameter, since using the same x everywhere, doesn't this correspond to having the same f over here?
So x is f.
Yes, so why do you need those different f's?
Okay, it could be the same. It doesn't really make a difference. It could be the same. If you like, I think the difficulty is not changed. Yeah.
So is the set phi of functions where the dichotomy that you had here earlier comes from, or no? Where you said for different.
Okay, I'll say what phi should be in a second. Yeah, so for k equals to 3, this is the Fourier set of Fourier characters. Mm-hmm. That would do. Any other questions? Yeah, so a bound like this will certainly be very nice. Even weaker bounds would be quasi-polynomial, or maybe even 2 to the n to the little 1 will be very, very nice. So we don't have anything like that. Okay. What we do know is, so we can take, for k equals to 3, so we essentially take the set of Fourier characters and can get a set of linear size. And for k at least 4, we can take phi to be of size 2 to the big O of n to the 1 minus k minus 1.
And what are these functions?
Okay, I'll explain. so here's a quick proof, just to get things started for k equals to 3. So when you learn Fourier analytic techniques in additive combinatorics, the first useful thing that comes, well, after Plancherel and all that, is the following identity that relates the number of 3APs with the Fourier coefficients. Okay, so there's this identity of this form. So this is an identity, and well, if I take absolute value and use Cauchy-Schwarz and Parseval, one finds that this is essentially controlled by the maximum Fourier coefficient. And what's a Fourier coefficient? A Fourier coefficient is a correlation with a Fourier character. And this is Fourier characters. And this essentially finishes the proof. If you don't like how some of the Fourier characters can be complex, that's an easy thing to deal with.
In general, so, non-classical polynomials don't.
Okay, so I'll say what it's okay. So if you know higher order Fourier analysis, so this certainly leads you to think that maybe we can use sort of generalizations of Fourier analysis. And the short answer is we don't know how to do this. So for general K, okay, so Fourier characters. So you can ask, what about quadratic Fourier characters? Or more generally, what about nil sequences? Well, if I'm allowed an extra, let's say epsilon, then I can use higher order Fourier analysis. But there's no extra epsilon there. So this is okay with higher order Fourier analysis, but without that epsilon, I don't know what to do. But still, I mean, it's a plausible, I think it's perfectly reasonable to suspect that if the Fourier characters for 3APs is a set of dual functions that I should look at, then maybe quadratic Fourier characters, or more generally nil sequences, should be the objects I should look at. It's just that we don't know how to prove that. That seems to be beyond our current understanding of higher order Fourier analysis.
So your purpose is even if you like for now, even if you lose an n to the epsilon in the right hand side of the inequality, that doesn't really change the bound at least right now.
Yeah, actually, so when we had this result, well, for our initial result for large deviations for APs, our first archive version, we actually, so we didn't do this. So we invoked the inverse theorem for Gauss uniformity norms, and that didn't give effective bounds. So this is in a very recent revision of the paper where we were able to obtain these polynomial type decays. Okay, so I have 10 minutes left. So what's the idea? The idea is that instead of explicitly coming up with, trying to do quadratic Fourier analysis, which at this point we don't know how to do for this problem, the idea is the following. Well, we want to understand, let's say, this quantity here. Okay, so I'll just say everything for 3AP, but this method works for AP of any length. We want to approximate, let's say for all G, this quantity here. But we can approximate it we don't have to know f on every value. And we only need to know f on a small set of coordinates. So by sampling f on around root n coordinates. So let's say if you do this randomly, give it a bit of extra slack, maybe some log factors, then just sampling f on this many coordinates will approximately recover this value simultaneously for all G. But then if I only care about f on about root n coordinates, then I just have to look at around n 2 to the root n possibilities for this approximate version of f, right, instead of O 2 to the n possibilities. And that's the major saving. I should mention that this idea is certainly not new. So this is a key part of Conlon and Gower's solution to Similarities theorem in a random set. And this also appeared more or less in a, okay, so what I'm about to say next, in fact, also appeared in this work of Frantzikanakis, Lessing, and Werdow on Similarities theorem with random differences. Turns out that instead of doing this randomly, it's somewhat better to use Chinese remainder theorem. Where choosing different primes has the effect that is analogous to choosing independent random variables. And so roughly the proof goes like this. I want to understand the dual function of f, so I define this function to be f. And okay, I want to estimate this quantity based on only a small set of values of coordinates of f. So now let me pick distinct primes p and q, both roughly of size root m. And I will write f, split up its support according to its residue class mod p and its residue class mod q. I'm going to write f as sum over r, sum over the different residue classes mod p, where here by f sub s I mean just separating the support, okay? Separating the support of f according to the residue class. And similarly, I also do this mod q. Let me decompose this function in the same way. What do I have? Well, I sum over r and s. And I just do this decomposition. So just that decomposition. So all the constituents here have distinct disjoint supports. If I normalize it this way, you'll notice that this quantity here actually is L infinity, so coordinate-wise bounded by Chinese remainder theorem. So that's a key observation. So this is analogous to choosing random variables and noticing that they are, for the most part, bounded once normalized. But doing Chinese remainder theorem doesn't give you any errors. It gives you very small errors. And so we'll just use these functions as our phi. So phi is not very large because each f is only supported on about root n coordinates. So there are only 2 to the root n functions I'm looking over. So each f here is supported only on, well, I only care about, each time only about root n possibilities. And okay, so that basically finishes the proof. I've done this for 3-term AP, but this exact same strategy with very minor modifications works for APs of any length, resulting in this expression here. As you can see, even for k equals to 3, what I get here is 2 to the root n, which is much worse compared to linear. But it does allow you to extend further. For k equals to 4, well, we don't know how to do any better than this. But you might remember that I also listed k equals to 4 as a special case in the bound for Gaussian width. And that's because we can get a slight improvement over this bound using not this method, but instead, here's an idea that allows you to do something slightly better for k equals to 4, which is to first apply Cauchy-Schwarz, and that reduces the problem from 4 APs to 3 APs on the finite differences of f. And then once you're down to 3 APs, now use Fourier. And Fourier is essentially efficient. Okay, so this is analogous to something, well, if you study the proof of Semmelweis theorem for 4-term arithmetic progressions due to Gowers, this is the kind of thing that comes up. And well, so this is certainly not the end of the story. Right? There's conjecture here, which seems to be quite difficult. And it seems to be just beyond the boundary of what we currently can do from higher order Fourier analysis. And I think it's certainly quite provocative. Is there something beyond or around higher order Fourier analysis that will allow us to understand the structure of the set of dual functions? I'll stop here.
Is the current lack of understanding regarding the higher order Fourier analysis a result of the poor bound to the inverse theorem at the moment? So if you had some super strong inverse theorem, would you be immediately done, or is there some further issue?
I think you still have further issues. Even if you have polynomial bounds, I don't think you can get quite what we want. But certainly that would be very nice. Yeah.
So what happens if you Cauchy-Schwarz for k equals 5?
Yeah.
Cauchy-Schwarz twice.
So it's worse than this. Yeah. So I thought initially that if you can do this, maybe that just means you can always save a step. But actually doing Cauchy-Schwarz is incompatible with this coordinate sampling. Right, so one way to think of it is that how do you sample? You can sample by projecting onto the Fourier coordinates, onto the Fourier bases. Or you can sample by projecting onto some coordinate bases. And these two operations are essentially incompatible. So this proof here is sampling onto the coordinate bases, whereas anything that uses the word Fourier is sampling onto the Fourier bases. Yep.
I don't quite know how you got to the Gaussian width question, but in the Gaussian width question, you're evaluating the gradients at all like 0, 1 y's, or I guess L infinity bounded y's.
Yeah.
Would the answer change much if you looked at the L2 bounded y's? So in other words, you're looking for the maximum receipt of this polynomial on a ball rather than in a...
Right, so okay, I will need to think about that. I don't have an answer right away.
Okay, I'll catch you.
Sounds good idea. 3:30.